This is Mrs. LaBarbera. This is AP Physics Mechanics C. Today's topic is various spring mass system in simple harmonic motion. The objectives are: no simple harmonic motion can occur in any system in which there is a restoring force, such as Fs equals negative Kx. Understand the motion of an object oscillating on a horizontal spring is simple harmonic. And also the motion of an object oscillating on a vertical spring is simple harmonic motion. Be able to derive the expression for the period of simple harmonic motion for spring mass system in vertical orientation. Be able to derive the expression for the period of simple harmonic motion for spring mass system with springs in series or in parallel. So we've learned in the last two videos that the motion of an object oscillating on horizontal spring is simple harmonic motion. We used Newton's second law, and we derived the differential equation, and from those equations we figured out angular frequency is square root of k over m, and x, the displacement, is sinusoidal function. This is really because the simple harmonic motion is projection of uniform circular motion projected on the diameter. Now let's consider motion in a vertical spring. So here is a spring that obeys Hooke's law. So over here is the equilibrium position. If a body is suspended from the spring, it is in equilibrium when the upward force is exerted by the downward force. And the new equilibrium position is here. So at this position, the upward force equals to downward force, mg equals to kl. If the body is displaced from equilibrium position, let's take a look at what is the net force. Net force is the sum of the forces. If we decide up is positive, so net force equals to upward minus downward. Since k times l equals mg, so this will give you negative kx. As you can see, the net force is proportional to the displacement and in the opposite direction as a displacement. This tells us this vertical vibration is a simple harmonic motion. And we only derive that when the body is moving above the equilibrium position. This equation, this relationship is also true when the body is moving below the equilibrium position. This is because the force is restoring. That means the force and the displacement are always in the opposite direction. So this equation tells us the mass oscillating in the vertical spring is simple harmonic motion. We can use Newton's second law to derive the mass oscillates with the same angular frequency as though it were in horizontal. Omega equals to k over m, square root of k over m, and t equals 2 pi square root of m over k. So what is the difference? There is essentially the same. The only difference is the equilibrium position is different. So by the way, equilibrium position for horizontal is when the spring is not stretched. Equilibrium position for the vertical is when the spring is in the new equilibrium position when the mass equals to, the weight of the mass equals to the spring constant, k times delta L. The same idea holds if the body with a weight mg is placed atop the compressible spring. So when the body is placed on top of the spring, it will vibrate in the simple harmonic motion with the same angular frequency and the same period. So let's consider this example. The shock absorbers in an old car with mass 1,000 kilograms are completely worn out. One 980 Newton person climbs slowly into the car to its center of gravity. The car sinks 2.8 centimeters. So from the force and elongation, we can find spring constant. When a car with a person aboard hits a bump, the car starts oscillating up and down in simple harmonic motion. Model the car and the person as a single body on a single spring and find period frequency of the oscillation. So from the force and the spring and the elongation, we can find the spring constant. From there, we can find a period. Remember, this is car and person, so we must add the mass of the car and the mass of the person in order to find a period. So this is addition, the sum of the mass of the car and the mass of the person. From there, we can find frequency. So persistent oscillation with a period about 1 second makes a very unpleasant ride. Mass spring system with spring in series or in parallel. Here is one spring. And from this one spring, we can figure out that T is 2 pi m over K. What if we connect this spring in series? So from our experience, we know it's much easier to pull the springs connecting in series. It's easier to pull. This is because the spring constant decreased. So the effective spring constant is this relationship, how you derive it. Okay, so when you find a new T, you have to use the combined effective spring constant. Since effective spring constant decreased, so T has to increase. The special case for this is these two have the same spring, so K and K connect together. In this case, the new equivalent spring constant is K over 2. So basically, the spring constant is cut in half. So the new T will increase because equivalent is decreased, increased by square root of 2. Connecting spring in series reduce the effective spring constant, resulting the longer period of oscillation. What happens if I connect the springs in parallel? You probably experience this. It's much harder to pull the two springs at the same time. This is because spring constant increases. And this is the equation to find equivalent spring constant. So because the spring constant increases, the period will decrease. So it's vibrate much faster than the single spring. The special case, if these two Ks are the same, in that case, the effective springs doubles. Effective spring constant doubles. So as a result, T will decrease by square root of 2. So connecting spring in parallel increase the effective spring constant, resulting shortened period of oscillation. Let's take a look at this example. A spring is mounted horizontally with K equals to 200 Newton per meter. A 0.5 kilogram glider is attached at the end. The glider is pulled at 2x equals to 0.2 meters to the right and released. It oscillates with T equals to pi over 10 seconds and omega equals to 20 radians per second. If another spring with the same spring constant is connected with the original spring in parallel, what is the new period? And write the equation for the displacement as a function of time. Since the spring is connecting in parallel, the effective spring constant increases, doubles. As a result, T decreases by square root of 2. Now, omega and T are inversely related. If T decreases by square root of 2, omega increases by square root of 2. So new omega becomes 28. The equation, since it's released from maximum displacement, this phi equals to 0. So the new omega x equals to A times omega t. If another spring with the same spring constant is connected with the original spring in series, what is the new period? And what is the equation for the displacement? Since when they connect in series, we know spring constant actually decreases. As a result, T increases. The spring constant doubles, T increases by square root of 2, and omega will decrease by square root of 2. So the new displacement is just simply put the new omega in there. Test your understanding. A block attached to a high ideal spring oscillates up and down with a period of 10 seconds on Earth. If you take the block and spring to Mars, where the acceleration due to gravity is only about 40% as large as on Earth, what will be the new period of oscillation? So let's take a look at the equation for period. This period only depends on mass and the spring constant. Since neither mass nor spring constant changes on Mars, so the T remains the same. Here is another example. A particle moves in simple harmonic motion represented by the graph. Which of the following represents the velocity of the particle as a function of time? From this graph, we know A equals to 4. Period is 2. We also know phi equals to 0 because you started from the maximum displacement. From t, we can figure out omega equals to pi. So this is just a function of omega, a omega t, cosine, function of cosine. So x equals a cosine omega t. So 4 is the a, omega is pi. But this one is asking you the velocity. Velocity is derivative displacement over t. So Vxt equals negative 4 pi sine omega t. The answer is E. Another example. A particle moves in a circle in such a way that x and y coordinates of its motion are given in meters as a function of time in t seconds by this. So as you can see, if this is moving, this is x component, this is y component. X component is omega, y component is x component is cosine, y component is sine. And theta equals omega times t, right? Because it's constant, omega. So in this case, omega equals to 3 pi and a equals to 3. So what is the period? T equals to 2 pi over omega. So in this case, 2 over 3 seconds. What is the speed? Speed is a times omega, right? Speed is rho omega, remember, is r times omega. In this case, r is the amplitude. So 5 times omega, that's 15 pi. And that's it for today. Thanks for watching.